formula. We know base voltage is really depending upon capacitors charging and discharging. So on state, how long the one transistor can stay in the on state. So that is equal to time to charge the base of Q2, right? This is the formula. T1 is the time to keep the Q1 in on condition. T1 is equal to 0.693 R1 C1, where R1 and C1 are the base circuit elements and it decides T1. So R1 C1, R2 C2, it decides how long this transistor should be on and how long this transistor should be on. Similarly for off state as well, the formula is the same. T2 is equal to 0.693 R2 C2. So based on these two things, so we are driving this Q1, base of the Q1, and then we are driving the base of the Q2. So if you calculate the total duty cycle or the total time, so T is equal to T1 plus T2. So this is the formula, right? So so if you add this together, and if you also assume R1 is equal to R2 is equal to R, if you use the same value R1, R2, for example, if I use 10 kilo ohm, I use the same 10 kilo ohm. If I use a 10 nanofarad, I use the same 10 nanofarad. C1 is equal to C2 equal to C, then we will get this formula. So this is the formula for the total timing of this astable multivibrator. We are talking about astable multivibrator. So what is the frequency of, why should we calculate this time first of all? Because we want to calculate the frequency of oscillation. So we know this astable multivibrator is also kind of oscillators. It's producing non-sinusoidal waveforms, right? So we need to know the waveform, the oscillations, how many cycle I produce per second, right? So if I want to calculate this one, then I must need to calculate the timing. So that is why we calculate the timing. So once we know the time, then oscillation is the frequency calculation is very easy. 1 divided by time. So 1 divided by T, that is equal to 0.72 divided by RC. This is the frequency of oscillation. If you want to change the frequency of oscillation, of course, you apply the value of R and C, then you will get some kind of numbers. Maybe this is 100 kilohertz. This is not the correct value, but I'm just telling for example. So if I use 10 kilo ohm, 10 nanofarad or something, I apply the value, then I can calculate the frequency of oscillation. The purpose, in practical design, you are designing the circuit for to apply in some application, to use in some application. So you are targeting to achieve certain oscillation frequency. So if you want to achieve 100 hertz, then you have to choose the correct RNC value. So for example, if I want to have this 100 kilohertz, then of course I can use this 100 kilohertz here, and then I can one value I have to assume and another value I can find using this formula. So the mathematical formula is very important in the circuit design. So this is the standard formula for this astable multivibrator. So the frequency of oscillation F is equal to 0.72 times 0.72 divided by RC. So this is the formula. So by this way, we can calculate the frequency of oscillations of astable multivibrators. So far we had seen the formula for this one. So one small problem for astable multivibrator, R1 is equal to R2 is equal to 5 kilo ohms, R1, R2 is equal to 5 kilo ohm, and RC1, RC2 is equal to 0.4 kilo ohm, RC1, RC2 is equal to 0.4 kilo ohm, C1, C2, they are 0.04 microfarad, C1 and C2 0.04 microfarad. Now find the time period and frequency of oscillation. This is one simple problem. Maybe you can solve this problem. So remember, here we have the RC1, RC2. You do not really use these values in the formulas. This is just to confuse you when you look at the problem. So we are not really using this. So you apply these values in the previous slide in the formulas, and then you will find the T, and then you will find the F. And you can check the answers later. These are the applications of Astable multivibrator. We can use this as a free running multivibrator to generate square wave frequency, and also as a timing oscillator or clock of a computer system. We can also use this Astable multivibrator to generate the clock signals. And also it can be used for flashing lights. Sometimes the flashing lights is on off, right? So we can drive the LEDs by using the output of this Astable multivibrator. So then you will have the flashing light at the output in the practical application. And also you can use this Astable multivibrator in switching and power supply circuits. So these are few applications of Astable multivibrator. So far, what we had seen, I think I want you to remember the basic design components like this we had seen, and then we had seen the circuit construction, and then we had seen circuit operation or working principle, and the output waveforms and formulas and applications. I took quite some time to explain this, but for the rest of the multivibrators, we can move faster because now you have some basic idea about the operation of the transistors and how you can make it short circuit or open circuit. Based on the short circuit or open circuit, the collector voltage will be there. So if it's short circuited, the collector voltage will go down to the ground. If it's open circuited, the collector voltage will get accumulated. So it can be logic 1 or logic low. So whatever the operation happening in this Q1, the opposite operation will happen in the Q2. If Q1 is on, Q2 will be off. If Q1 is off, Q2 will be on. So always the opposite. So we have two output terminals, O1 and O2, output 1, output 2. If the output 1 is logic 1, output 2 will be definitely logic 0. And here is 0 and this is 1. So this is automatically changing the status, the state from this is state 1, that is logic 1. This is state 2, logic 0. So it's changing automatically the output. So that is why we call this as an Astable multivibrator. The formulas are very simple. Try to remember that. And the problem, you can solve that. So you will remember the formula if you use it. And these are some applications.